Am I audible? Okay, Jit. Jit, be fine. So we continue with some more examples of recursive definitions. And next one is recursive definition for set A of all strings in 0, 1 star not containing substring 0, 0. So my sigma is 0, 1. The sigma star will be 0, 1 star. So various combination of zeros and ones. Set A contains strings having different combinations of zeros and ones of any limit, of any length. We want to recursively define that. This is little tricky definition. Not containing substring 0, 0. The shortest string would be here in set A. The shortest string would be, any guess? Okay. Look at the definition. Of course, the shortest string is null, not containing substring 0, 0. So null is the shortest string, length 0. Of length 1, 0 and 1 both will be there. Yeah, Abhi, 0 is there. Prior to that, even null is there because 0, 1 star. So null is element of sigma star. So null will be shortest of length 0. 0 is length 1. Abhi, string length of 0 is 1. So 0 is there. Its length is 1. It is there. Even 1 is there. But we are covering 1 in the next part. We are not separately writing 1. There is no need to separately write that. So for x belonging to A, both 1x and 0, 1x belong to A. Or this is also fine. So 1x, when I say 1x and put null for x, that will include 1. So null, 0, 1, they are there. And not containing substring 0, 0. So here in rule number 2, let us look at this part only. In rule number 2, after 0, we are putting 1 to ensure that substring 0, 0 is not present. In 1x, this first part, for x belonging to A, both 1x. So after 1, we can have anything in x, but anything except 0, 0. So if the string start with 0, then my next symbol is 1. So that it is ensured that there won't be repetition of 0. There won't be 0 after 0. There won't be substring 0, 0. So after 0, 1 is there. X can be anything. But then again, in that anything, it is ensured that after 0, there is always 1. And various combination of 1s, that any number of 1s is fine. So after 1, x is fine. After 1, if I can put, I replace in that 1x, after 1, if I replace x with 0, then after 0, 1 has to be there. So whichever combination are there, after 0, 1 is there. And then I can have x, 0, 1, x. I can paste x. So 0 is taken in rule number 1, 0 is taken separately. And in rule number 2, after 1 I am writing x. So again 0, 0 is avoided. In 1x, after 1 I am writing x. X could be 0, that's fine. And before x, 0, 1x. Before x I am putting 1. So two things are there. After 0, 1 is there. And before x also 1 is there. So even if I copy paste x containing 0, it is ensured that 0, 0 it is not present. So that is how the substring 0, 0 is eliminated. Combinations of the substring 0, 0 is eliminated by writing 1x. So before x 1 is there. And 0, 1x also, in 0, 1x also it is 1 before x. And in 0, 1, after 0 I am putting 1. So that is how all the possible combinations of zeros and ones not containing substring 00 is taken care. Maybe I can write this as x1 x10. That is also fine. Instead of 1x 01x, I can write x1 x10. So immediately after x, 1 is written. Immediately after x, 1 is written. And after 1, 0 comes. After 1, 0 comes. So x may be copy pasted. Could be anything. Anything means not containing 00. And then after x, I am putting 1. So even if x is ending with 0, I don't have two zeros. x10 or x1. So instead of 2, we can write rule number 2 in this way also. Even in this particular case, if we combine 2, 1x, 01x, x1, x10, if all the 4 possible combination we write, still it is ensured that we don't have 00. There's no need to write it. So whenever such things are there, normally we'll avoid writing these combinations because we don't know if there are more the combinations, more the possibility that I ignore some of the options. So it's better to write either 2 before or, rule number 2 before or, both 1x and 01x, or write x1 x10, just to ensure that by mistake we don't have illegal combinations included. In this particular case, even if we club, it is taken care that 00 won't come. Even if we write 1x 01x x1 x10, still it is taken care, but normally we'll avoid that. Either of these is fine. It will generate all the strings containing not 00. That is taken care. So that is our definition, recursive definition for the set A. Is that clear? Is that clear? B fine. Any other student? No more answer? Cable, that is fine. Okay. Love fine. Rikin fine. Okay. Now we go to one more proof on string using PMI. The statement is strings of the form 0y1 must contain the substring 01. Strings of the form 0y1. So we are again reverting back to proof. We have seen some of the recursive definitions. In the next statement that we are going to prove on using PMI, it is on strings. And the statement is strings of the form 0y1 must contain the substring 01. Earlier we have put, just going back to that, this was one more proof on strings. We defined recursively language L, and L, that is of the form 0 raised to I, 1 raised to j, and we have proved that A is a subset of L for every string of this form 0 raised to I, 1 raised to j. It is in L. So that particular statement on strings we proved using PMI. One more statement we are taking, and here is the statement. 0y1, to take the pattern, it contains substring 01. That's the statement. Strings of the form 0y1 must contain the substring 01. This is our statement. So another example of a proof using PMI involving strings. So one more example of proof on strings using PMI. And the statement is strings of the form 0y1 must contain the substring 01. That's the statement. Once more, we don't have integer n present. Once again, we take length of the string as our integer n. The induction is on the length of the string. The induction is on the length of the string, and here is the statement Pn. If length of x equal to n, we are explicitly introducing n. If length of x is equal to n, and x is equal to 0 y1 for some string y belonging to sigma star, then x must contain the substring 0 1, and we'll prove this for n greater than equal to 2 because we are talking about pattern 0 1. So obviously length of x is at least 2. Pn is the statement, length of x equal to n. In our original statement, n was missing. While dealing with strings, we may think about, most of the times we'll think about taking n as length of a string. So we say x equal to 0 y1 for some y belonging to sigma star, and length of x equal to n. X must contain the substring 0 1. This is our statement. Length of x equal to n. X equal to 0 y1 for some string y belonging to sigma star. X must contain the substring 0 1, and we'll prove this for n greater than equal to 2. We are talking about the substring 0 1. So length of x is at least 2. We'll prove this statement for n greater than equal to 2. So prove the basis, write the basis. P of 2 is true. N equal to 2, that is my basis, that is P2 is true. That is, replace n with 2. Length of x is 2. X equal to 0 y1. For some string y belonging to sigma star, x must contain the substring 0 1. Starting value of n is 2, that is my basis, and according with the statement. Length of x is 2. X is equal to 0 y1 for some string y belonging to sigma star. X must contain the substring 0 1. How do we prove this? Sorry. How do we prove this? Keval, how do we prove this? Now length of x equal to 2 and x equal to 0 y1. From this 2, it means y is null. Length of x equal to 2 and x equal to 0 y1. So in this case y is null. So x equal to 0 1, and it contains the substring 0 1. So that is as simple as that. Length of x equal to 2, x equal to 0 y1 implies y is null and x is equal to 0 1. Length of null, that is equal to 0. So 0 null 1, that is 0 1. Therefore x contains the substring 0 1. That is obvious. And maybe we don't have too many assumptions required. Probably we are looking for substring 0 1 in 0 y1. So we can try out, we can take a chance with the weaker form of PMI. K greater than equal to 2 and P of K is true. So that length of x, this statement, length of x equal to n, as we are taking the weaker form of PMI, it becomes length of x equal to k. So that is our statement. K greater than equal to 2 and pk, that is length of x equal to k, and x equal to 0 y1 for some string y belonging to sigma star, x contains the substring 0 1. Yes, this is weaker form of PMI. We are not saying length of x equal to n. We are saying that length of x is equal to k. Only one assumption. The statement is true for n equal to k. That's it. Accordingly, the hypothesis statement, length of x is equal to k plus 1, and remaining things as it is. Length of x equal to k plus 1 and x equal to 0 y1 for some y belonging to sigma star, then x contains the substring 0 1. Now the proof. length of x is equal to k plus 1 and x equal to 0 y1, which means length of y1 is k. This is observation number 1. Length of x is given to be k plus 1 and x equal to 0 y1. So if you remove 0, then remaining string is y1. So length of y1 is k. Total length is k plus 1, 0, then y1. So length of y1 is k and length of 0 we know it is 1. Total length is k plus 1. So length of y1 equal to k, that is observation number 1. Now k is at least 2. K is at least 2. K greater than equal to 2. And length of y1 equal to k. It means y is not null. Length of y1 equal to k. K is at least 2. Therefore, y cannot be, the string y cannot be null. Y is not null. That is our observation number 2. And because y is not null, we can say y begins with either 0 or 1. Till now, we have proved that y is not null, and because it is not null, it is beginning with either 0 or 1. This is next inference. Y begins with either 0 or 1 as it is not null. Again, we have to prove the statement, and maybe once more we think about dividing the proof into the cases approach. So far we have inferred that y begins with either 0 or 1. So straight away let us put the cases as y begins with 1 and y begins with 0. These are our cases. We are taking once again dividing the proof into the cases approach. Y begins with 0 or 1, and the cases are y begins with 1 and y begins with 0. Dividing the proof into the cases. So y begins with 1. X equal to 0 y1. X equal to 0 y1 and y begins with 1. We are looking for the substring 0 1 in x. Y begins with 1. It means 0 1 is present in x as its prefix. 0 y1 and y begins with 1. So that becomes 0 1 something and 1. So in x, the substring 0 1 is present as its prefix. This is the very simple case. X equal to 0 y1, y begins with 1. So 0 1 is present in x as its prefix. 0 1 is present as its prefix. We talk about x. We are looking for substring 0 1 in x. In this case, it is present as its prefix. 0 y1, y begins with 1. So it becomes 0 y, 0 1 and something, and last character is 1. So that is proof for case number 1. Very simple. That's the reason we have divided the proof into the cases. Now the second case, y begins with 0. Y begins with 0. Length of y1 earlier equal to k, and k is at least 2. K is greater than equal to 2. Length of y1 equal to k. Y begins with 0. Case number 2. In total length of x, length of y1 is greater than equal to 2. Length of y1 is greater than equal to 2 because length of y1 is k and k is at least 2. So length of y1 is greater than equal to 2. My x is 0 y1. Total length of x is k plus 1. Length of y1 is k. K is at least 2. Therefore length of y1 is greater than equal to 2. In fact, length of y1 is k. And why we categorically state that? Here, length of y1 is k. Also, y1 begins with 0. This is y begins with, this particular case, y begins with 0. Therefore, the entire string y1, it begins with 0 and ends with 1. Now our focus is in y1. Now y begins with 0. Length of y1 is k. It means the structure of y1 is something like this: 0, z1. Length of y1 is at least 2. So I can write y1 as 0, z1, because in this case y begins with 0, it is ending with 1. Y begins with 0 and y1 ends with 1. So the structure of y1 is 0, z1 for some z belonging to sigma star. For some z belonging to 0, 1 star. Why do we state this? Let us go back to why do we conclude this? Just go back to the hypothesis. If I want to use hypothesis, then I must have a string length of x equal to k, any string whose length is k, and the structure of the string has to be 0, y1 for some string y belonging to 0, 1 star. So here, under this case, we are establishing that the structure of y1 is 0, z1, because y begins with 0, then remaining characters, and then ends with 1. Length of y1 equal to k. Length of y1 is at least 2. It means I can write y1 as 0, z1 for some z belonging to 0, 1 star. So the string y1 has the structure 0, z1 required for using the hypothesis. Length equal to k, and it is of the form 0, z1. Once that is established, I can use the conclusion part of the hypothesis. Then x contains the substring 0, 1. It means y1 contains the substring 0, 1. Prerequisite for hypothesis is specified, is verified. Now I can use the conclusion of the hypothesis, which is y1 contains the substring 0, 1 using the induction hypothesis. And my x is 0, y1. So automatically x also contains the substring 0, 1. That is my conclusion. In fact, that completes the proof for case number 2. Therefore, x equal to 0, y1 also contains the substring 0, 1. That completes the proof for case number 2. Case number 1, y begins with 1. We proved. Then y begins with 0. That also we proved. So we categorically focused on y1 because that particular string has length k. Given that x has length k plus 1, x equal to 0, y1. So when we focus on y1, then its length will be k, because ultimately I want to use the hypothesis. For easily proving the statement, I am using hypothesis. Therefore, I focused on y1 because that's length is k. Length of y1 is k. And then I went for dividing the proof into the cases. We can say y1 begins with 0, begins with 1, that is also fine, or maybe y begins with 1 and y begins with 0. Those are our cases. Under both the cases, we proved that y1 contains 0, 1. Therefore, x also contains the substring 0, 1. That completes the proof. That completes the proof. Now we say cases were y begins with 0, y begins with 1. We could have also focused on y ending with 0, y ending with 1. That is also fine. Here we said y begins with 1 and y begins with 0. Maybe we could have also thought of y ending with 0 or y ending with 1. Then under that case also, we could have easily proved the statement. This can also be proved by taking string of the form y1. Its length is also k, and the cases would be y ends with 0 and y ends with 1. Y ends with 0 and then y ends with 1. Y ends with 1. So y ends with 1 means my x is 0, y1. So again, I will get something like 0, z1. Very similar to what we got in these cases. Is that clear? Is the proof clear? Is it clear to all? Keval? Is it clear to other students? Abhi, fine. Only two responses from Keval and Abhi, only two responses. Janil, okay. Any doubt? Begin, fine. Okay. So this was another example, one more example. We proved statement involving string using PMI. So whenever we deal with string, many times we will take length of the string as induction variable. The induction will be on length of string. That is our integer n that we are looking for. Most of the times it won't be given in the statement. Again, here in this statement, the length of string x, that is not given. So we have taken x equal to 0, y1 and length of x equal to n. That is how we formulated statement Pn and then proved using dividing the proof into the cases approach. But if you want to use the hypothesis, then the prerequisite, for example here, length of x equal to k, x equal to 0, y1 for some string y belonging to 0 star, sigma star. I must establish that. Then only I can use. If I don't show the prerequisite, then whatever you claim does not make any sense. That will be incorrect. That won't be acceptable. So here, case number 1 was our simple case, where directly we get 0, 1. In case number 2, we have to show that the prerequisites are satisfied. Length of x equal to k, x equal to 0, y1 for string y belonging to sigma star. I must explicitly show that. So in case number 2, here length of, we talk about length of y1 because my x was 0, y1. Total length is k plus 1. So length of y1 is k. So that particular prerequisite, length of x equal to k, length of x equal to k in this hypothesis, I satisfied by writing x equal to 0, y1 and then focusing on y1. Then focusing on y1. I can also focus on 0, y. In that case, again length is k. 0, y, I can have that. Instead, I prefer to talk about y1, length is k, and then its structure has to be 0, y1. For string y belong to sigma star, then I can conclude it contains substring 0, 1. So here, in case number 2, case number 1 was straightforward. I showed that its structure is Z0, Z1. So I have to talk about the length. I have to say that k is at least 2. Then I can write y1 equal to 0, Z1. If length of y1 is at least 2, then only I can write y1 equal to 0, Z1 for z belonging to sigma star. So that second and the third requirement, length equal to k, length of y1 equal to k, and the structure of y1 is 0, Z1. That I explicitly showed that its structure is 0, Z1. And once these two prerequisites are satisfied, then I can conclude y1 contains substring 0, 1 using hypothesis. If I don't show the satisfaction of the prerequisite and directly you say using hypothesis, that will be treated as wrong. That will be treated as wrong. It might look obvious, but you have to argue formally. It's very important to formally argue. Whatever we claim is not acceptable unless it is formally proved. So sometimes the things might look simple, but unless we formally prove that, it's not acceptable. So whenever you, particularly for some research kind of statement, for some new statement, whatever we claim needs to be formally proved. That is the importance of these formal proofs. May not sound very, very interesting, but it is very, very important. It's very important. Fine. Next, language L. Let's prove that L is a subset of A using a very different induction variable. A was earlier. Language L, we recursively defined language L. A was of the form 0 raised to I, 1 raised to j, I greater than equal to j greater than equal to 0. Now we show that earlier we have proved A to be a subset of L. We proved A to be a subset of L. Let's go back to that definition once again. This one. So this was our language frequency definition. 0y and 0y1 are in L. L contains strings of the form 0 raised to I, 1 raised to j, and we showed that A is a subset of L. We had shown that A is a subset of L. Now we'll show converse L to be a subset of A. The converse of the statement. We have proved A to be a subset of L. Now we'll prove L to be subset of A using a very different induction variable. Here also, in this case, we have taken induction variable as length of string. Both the examples that we have worked out till now, in them, the induction variable is length of string. Now we'll use a different induction variable. We'll use a different induction variable in the next proof. Converse of the statement L to be a subset of A. So that's a converse statement proving using different induction variable. L to be a subset of A, converse of the statement using a very different induction variable. Can anyone guess what could be the induction variable other than length of string? We want to prove L is a subset of A using a different induction variable. Can anyone guess what could be the induction variable other than length of a string? Any guess? Here, we'll take induction variable as number of times rule 2 applied in generating a string in L. That will be our induction variable. A very different induction variable. Number of times rule 2 applied in generating an element in L. That will be our induction variable. Definition of this is my L. So how many times we apply rule 2 in generating element in L? That will be our induction variable. That will be our integer n that we are looking for. Number of times application of rule 2, that will be our n that is required in PMI. Number of times rule 2 is applied in generating x in L. Of course, we can prove this using length of x. Like earlier two cases, we can prove using length of x. However, just to show that the induction variable could be different, here we are taking number of applications of rule 2 in generating x in L. That is our integer n. So for every n greater than equal to 0, every x belonging to L obtained by n applications of rule 2 is an element of A. We are proving L to be a subset of A. So how many times we apply rule number 2 in generating x in L? That will be our integer n. So for every n greater than equal to 0, every x belonging to L obtained by n applications of rule 2 is an element of A. L is a subset of A. How x is generated in L? N applications of rule 2. And we say that n is greater than or equal to 0, even equal to 0, because even by not applying rule number 2, we can generate a string in L. Null belongs to L, and null does not require any application of rule 2. Therefore, value of n is greater than or equal to 0. Even 0 applications of rule 2, that is also fine. Am I audible? Am I audible? Okay, let me once again share this. How much? I don't know. Keval, was I audible for the last proof? Last proof, did I completely explain that? Last proof? Keval, you can unmute and answer me. A lot of time is wasted.
Yes, sir. Sir, you are talking about L is a subset of A that we proof started. Yes,
Okay,
from here. Yes.
up to that point, it was audible, no?
Yes, sir. Yes, sir.
Okay, fine. So induction variable, it is number of applications of rule 2 and n starts with 0 because even if I don't apply rule number 2, still I can generate a string in L using rule number 1 because null belongs to L. Let's see. Even if I don't apply rule number 2, what is my n? Number of times we are applying rule number 2 in generating x in L. So even if I don't apply rule number 2, still I can generate x in L because null belongs to L. Therefore, the starting value of n is 0. We prove this for n greater than or equal to 0. 0 application of rule 2. It means 0 application of rule 2 means null. And we have to show that null belongs to A. L is a subset of A. Number of times we apply rule number 2 in generating x in L. Starting value of n, that is equal to 0. So 0 application of rule 2. It means I'm applying rule number 1. It means I'm talking about x equal to null. And I have to show that null belongs to A. And I can show here because 0 raised to 0, 1 raised to 0. That will be my null. And that belongs to A. 0 application of rule 2. It means x is null. And null belongs to A because this is 0 raised to 0 and 1 raised to 0. That is how it is present in A. So that is my proof for basis. This is proof for basis. X is obtained by 0 applications of rule 2. X is null and it is present in A because null equal to 0 raised to 0, 1 raised to 0. And we are talking about number of times we apply rule number 2. So once again, weaker form of hypothesis, weaker form of PMI may be sufficient because that will be K application and then K plus 1 applications. I don't require assumptions for multiple values. So once again, I go for the weaker form of PMI. K greater than equal to 0, and every string in L, every string X in L that can be obtained by K applications of rule 2 is an element of A. So hypothesis, we have decided to go for the weaker form of PMI. So we state that again in both the cases we have to specify range of K. Range of K is same as range of N. So K is greater than equal to 0. And every string X in L that can be obtained by K applications of rule 2. We are not talking about N applications. We are talking about K applications. It means it is a weaker form of PMI. Every string in L that is obtained by K applications of rule 2 is an element of A. And in the induction statement, K plus 1 applications. Any string in L that can be obtained by K plus 1 applications of rule 2 is in A. That is my induction. So let X be an element of L that is obtained by K plus 1 application of rule 2 in L. X is an element of L that is obtained by K plus 1 applications of rule 2. It means X is either 0y or 0y1 and Y is obtained by K applications. X is obtained by K plus 1 applications of rule 2. And rule 2 is what? Take a string, then new string 0y, 0y1. That is also element of L. That is my rule 2. So if X is obtained by K plus 1 applications of rule 2, it means X is 0y or 0y1, where Y is obtained by K applications. If Y is obtained by K applications, then when I apply the rule number 2 one more number of time, that is K plus first time, then the new string is 0y or 0y1 as per the definition. So as X is obtained by K plus 1 applications of rule 2, X is of the form 0y or 0y1, where Y is obtained by K applications of rule 2 in L. Now actually this becomes a simpler proof. Y is obtained by K applications of rule 2 in L. Let us go back to our hypothesis. Here itself, K greater than equal to 0, every string in L that can be obtained by K applications of rule 2 in L is an element of A. Here, Y is obtained by K applications of rule 2 in L. It means the prerequisite for the hypothesis is satisfied and we can derive that Y is an element of A. Y belongs to A. Any string in L that can be obtained by K applications of rule 2 is an element of A. We have established that Y is obtained by K applications of rule 2 in L. Therefore, Y is an element of A. Y belongs to A. And once Y belongs to A, I know anything that belongs to A, it means it is of the form 0 raised to I, 1 raised to j, where I is greater than equal to j, greater than equal to 0. We have shown that Y is an element of Y is an element of A using our induction hypothesis, because it is in L, it is obtained by K applications of rule 2 in L. Therefore, using hypothesis, Y is an element of A. Y belongs to A. And once Y belongs to A, it means Y equal to 0 raised to I, 1 raised to j. I greater than equal to j, greater than equal to 0. That is my A. Set A equal to, within curly bracket, 0 raised to I, 1 raised to j, I greater than equal to j, greater than equal to 0. Here, we have inferred that Y belongs to A. Therefore, Y has to be of the form 0 raised to I, 1 raised to j, I greater than equal to j, greater than equal to 0. Ultimately, we have to show that X belongs to A. We have shown till now that y belongs to a, but not x. So let us, what is x? My x is 0y or 0y1. So x is 0y or 0y1. So y equal to 0 raised to I 1 raised to j, and x equal to 0y. It means x equal to 0 raised to I plus 1, 1 raised to j. Y is 0 raised to I 1 raised to j. In first case, x equal to 0y. So it is 0, then 0 raised to I, 1 raised to j. That becomes 0 raised to I plus 1, 1 raised to j. And definitely, because I is greater than equal to j, I can say I plus 1 is also greater than equal to j, which is greater than equal to 0. Once these things are established, structure of x is 0 raised to I plus 1, 1 raised to j, where I plus 1 is greater than equal to j, which is greater than equal to 0, I can safely state that x belongs to a. My a is 0 raised to I, 1 raised to j, I greater than equal to j, greater than equal to 0. I have shown that x equal to 0 raised to I plus 1, 1 plus 1 raised to j, where I plus 1 is greater than equal to j, which is greater than equal to 0. Therefore, x belongs to a. Similarly, in the second case, 0, y1. Y is already 0 raised to I, 1 raised to j. To that, I am putting one more 0 at the beginning and 1 at the end. So that becomes 0 raised to I plus 1, 1 raised to j plus 1. And because I is greater than equal to j, I am adding 1 to I and adding 1 to j. Therefore, I plus 1 is greater than equal to j plus 1, which is greater than 0. I am adding 1. So earlier I was greater than equal to j, greater than equal to 0. So here I plus 1 greater than equal to j plus 1, which is greater than 0. But if it is greater than 0, I can always say it is greater than equal to 0. Once again, in second case, x equal to 0, y1, I have shown that the structure of x is such that it belongs to a. So in both the cases, x belongs to a. That was the statement to be proved. That was the statement to be proved. Any string in L that can be obtained by k plus 1 applications of rule 2 is in A. That was our x in L obtained by k plus 1 applications of rule 2, where y is obtained by k applications of rule 2. We have shown that y belongs to A, and once y belongs to A, my x, which is 0y or 0y1, they also belong to A. That completes the proof. Any doubt? Is that clear? Is that clear? Keval, that is fine. Any other? Abhi, that is okay. Any more? Harsh, Tumar, that is fine. Good. Any question? Say please. It is very important to prove these statements. We are not studying this subject for just doing some small mathematical calculations. It's not a part of mathematics. Here we must learn a way to formally justify an argument. So you may feel that no, it's little difficult and it's not as simple as doing some working out some examples. This is not for here. Basically, we are not learning to work out an example. Here we are learning to formally prove a statement, formally argue a statement. Using given things, formally argue a statement. That is how we learn to justify our claim. It is important to justify our claim. Even if you are working in some say R&D organization, later on, in a company or maybe abroad. So whatever statement you make requires formal justification, formal argument. May not be this much formal, still requires formal justification. So don't stay away from proving certain statement. Proof is very important. Whatever we claim has to be proved. That is very important. So it's not for interest, it's for the requirement. Proving is for, we are not learning this for our interest. We are learning this for requirement. We are learning a formal approach is for proving claims, proving statements. Fine. Any doubt? Otherwise, we move to version of induction. So far we have studied the weaker form of PMI and the stronger form of PMI. In a representation different, actually there's a representation difference in PMI in what is called structural induction. Here we have different representation than our conventional PMI in structural induction. What is that? Let's see. This is an induction proof based on the structure of the definition, structural induction. So here we'll not categorically mention N, but directly go to the structure of the definition and then prove a statement. N will not be explicitly specified in structural induction. It is not required to explicitly specify integer n in structural induction, though implicitly it is present, because that n will come from the structure of the definition. Here, integer n is not explicitly used. And let us go back to the last proof itself. The last proof using structural induction. Already we have proved L is a subset of A using conventional induction. This is conventional induction using the weaker form of PMI. And we introduced explicitly, we took n to be number of applications of rule 2. That was our n. Now the same proof we prove using structural induction. It will look little informal, otherwise it is not. Let's see what we are trying to say. L is a subset of A, that is to be proved. So our definition, rule number 1, null belongs to L. Go back to the definition of L. This proof is based on the definition of the given language. So in that, rule number 1 is null belongs to L. Rule number 2 was our 0y and 0y1. Rule number 1, null belongs to L. So here we are proving L to be a subset of A. And as per the definition, null belongs to L. Therefore, here we have to show that null belongs to A. That's it. We must show that null belongs to A. We are not writing explicitly that null is obtained by zero application of rule 2. Though we are not writing, it is there. Zero application is there. Therefore, we are talking about null. So straight away we show that null belongs to A. That becomes our basis. And this is true. Proof again remains the same. Proof for the basis remains the same. Way of representation is different. That was our basis. X is obtained by zero applications of rule 2 is an element of A. And then we showed that null equal to 0 raised to 0, 1 raised to 0 belongs to A. Exactly same proof. Only those statements we are not writing. We are taking n implicitly, or n depends upon the definition, structure of the definition. So we show in basis that null belongs to A. This is my basis. We must show that null belongs to A, and proof remains same. Basis is over. To prove L is a subset of A, structural induction proof, basis, null belongs to A, proof remains the same. Similarly, hypothesis, the string y belongs to L is an element of A. The string y is assumed to be element of A. Again, we are not stating that y is generated in L by k applications of rule 2. It is assumed, because in the induction statement we talked about 0y and 0y1. X is obtained by k plus 1 applications of rule 2. X is 0y or 0y1, where y is obtained by k applications of rule 2. So here we don't specify that values. We say in the hypothesis the string y belongs to L is an element of A. And in the induction statement, from y what we get? 0y or 0y1. That becomes our induction statement. Both 0y and 0y1 are elements of A. Proof remains same. Y belongs to L. Y is an element of A. That is the hypothesis. So y equal to 0 raised to y, 1 raised to j. Same proof. Absolutely no change in the proof. Same here. Here we categorically show that y is, because it is obtained by k applications of rule 2 using hypothesis, y belongs to A. And then we talk about the structure. Here directly we talk about the structure. Y belongs to A. Y is an element of A from the hypothesis, therefore y equal to this. And x is my 0y or 0y1. So x is this, it belongs to A. Same argument. For 0y and 0y1 to be in A, same argument. This one, this I plus 1 greater than equal to j greater than equal to 0 in first case, and I plus 1 greater than equal to j plus 1 greater than equal to 0 in the second case. In both the cases, x belongs to A. So that completes my structural induction proof. It may look very informal, it is not, because n is implicitly present. When we say null belongs to A, it means null is obtained in L using zero application. That is there in the basis. Hypothesis, we say y is an element of A, and then we switch over to 0y, 0y1. So entirely the proof is based on the structure of the definition. Therefore, it is called structural induction. Therefore, it is called structural induction. That was our rule number 1 we used in the basis. Then y belongs to L. Y is an element of A. That particular part we used in the hypothesis. And then based on the structure, we have to show that 0y and 0y1, they are element of A. And that we showed. So though n is not explicitly present, proof may look very simple, maybe informal. It is not. It is not. Is that clear? Structural induction, is that clear? Keval, Love, few more responses. Abhi, fine. Harsh, Tumar, fine. Okay, so actually we are done with most of the topics required for your internal exams. I have a couple of lectures left in offline mode. So depending upon how much I am able to cover in that, maybe I think half an hour or so extra lecture may be required in your class. So I'll announce that later. Let me see in the offline mode how much I am able to cover. Topic wise, everything is over. Maybe a few examples we can work out, like this, more example on structural induction. Then a proof, examples in the proof in structural induction. One more definition and maybe proof. If I cover that in the other class, I'll take extra lecture maybe on Saturday around 45 minutes. If I'm not covering these examples in the other class, then this is fine. Topic wise, the syllabus is over. Okay, fine. Thank you.